Howdy. Today I'll be solving the final exam for Physics 207 from 2019 to hopefully help prepare for the upcoming final. So let's get started. So the first problem, regardless of the professor you have, is going to be to write down Maxwell's equations in integral form. And we need to know that there's 4 of them. And the first one is Gauss's law, which is the flux of E dot ds is equal to Q enclosed over epsilon naught. And the second one is Gauss's law for magnetic fields, which is the flux of B dot ds is equal to 0. The third one is Faraday's law, which is the closed loop of E dot dr is equal to negative partial with respect to time of the flux of B dot ds. And the last one is Ampere's law with Maxwell's modification, which is closed loop of B dot dr is equal to mu naught I plus ID, where ID is displacement current, but you have to write ID in its full form, so it's mu naught I plus epsilon naught times the time partial derivative of the flux of E dot ds. And these are the 4 equations you need to know for this entire exam, pretty much, because we're going to be using them the entire time. So let's go to number 2. An insulating sphere, okay, so it's an insulator of inner radius A and outer radius B has a uniform charge density rho. It is surrounded by a spherical conducting shell of inner radius C and outer radius D. A point charge Q naught is placed at the center as shown, so there's a point charge of Q naught in the middle. We want to find the electric field everywhere, pretty much. So for this problem, we're going to use Gauss's law, which is the flux of E dot ds is equal to Q enclosed by our Gaussian surface divided by epsilon naught. So for R less than A, we're going to be in this region right here. So we're going to have E, and then the area of the sphere, which is 4 pi r squared, this is equal to the charge enclosed, which is just a point charge Q naught divided by epsilon naught. So then solving for E, we just get Q naught over 4 pi r squared epsilon naught, and we have to indicate the direction. This is radially out because it's a positive. If it was negative Q naught, or if anything was negative for that matter, it would be radially in, but because it's positive, it's going to be radially out. So now for the next region, between A and B, and put this in green, I'm in here now. And the problem said this is an insulating sphere with uniform charge density rho. So to solve this, we're going to have E, the left side's always going to stay the same, so long as it's still a sphere. E 4 pi r squared is equal to 1 over epsilon naught. And it's typically the charge divided by actual volume times Gaussian surface volume. So charge per unit volume, which is the actual volume here, this is given as rho, so we don't need to worry about this. But all we need to do is multiply rho by the volume created by our Gaussian surface. So we're going to have rho times the volume of where our Gaussian surface is. Now our Gaussian surface doesn't enclose the entire insulator, it just goes up to a radius of r, right? So it's going to be 4 over 3 pi r cubed minus 4 over 3 pi cubed, right? Because we need to account for this hole right here, because we only care about where the insulator is. But then we also are enclosing the Q naught point charge in the middle, so we have to add Q naught as well. So then solving for E, we'll get 1 over 4 pi epsilon naught r squared of rho 4 over 3 pi r cubed minus 4 over 3 pi a cubed plus Q naught. And again, this is radially out. And again, we have to enclose both of them because it's what our Gaussian surface is enclosing. So our Gaussian surface is including the insulator that's in the green lines, but then it's also including the first electric field we found earlier. So now for the second one, when B is greater than C, we are right here. So in this case, we are going to cover the entire insulating shell. So it's basically going to be the same thing that we got for this part, but instead of 4/3 pi r cubed, it's going to be the actual max radius of that insulator, which is going to be B. So then E, which is going to be 1/4 pi epsilon naught r squared of rho 4/3 pi b cubed minus 4/3 pi a cubed plus q naught radially out. And again, this is because our Gaussian surface is now enclosing the entire insulator. Insulator has a max radius of B. This is B, and this is radius A. So, yeah. So now for the next region, between C and D, we are right here. Now remember that the problem said that there is a conducting shell of inner radius C and outer radius D. So right now we're inside the conductor, and we know that the electric field inside of a conductor is 0. So this is simply 0. It's a conductor. Now lastly, for our last region, when R is greater than D, do that in blue. We're out here. And because the problem doesn't say that the conductor has like a charge Q naught or negative Q naught or any charge residing on it, this answer is basically going to be the same thing as the one up here. Because there's no plus Q naught or something that the problem said. So we can assume it's neutral. So then the answer for the last part is going to be E is equal to 1/4 pi epsilon naught r squared of rho 4/3 pi b cubed minus 4/3 pi a cubed plus q naught radially out. Okay. Now for part B, assuming that q naught is 0. So now we're assuming that the point charge of the center is now 0. Find the difference in electric potential between a point r equals P and r equals M. And it writes it out right here. So recall that the difference in electric potential is V of R2 minus V of R1 is equal to the negative, forget about the negative, integral of R1 of R2 of E dot dr. So we're going to have V of M minus V of P is equal to the negative integral from P to M of E dot dr. But now we need to break up this integral because our electric field is different for different regions, right? So we start at P. Let's see where P is at. So P is at the region between B and C, right? The one in red. So my integral is going to start at P, and it's going to go up to the point before the electric field changes. So because I'm in between P and C, my first integral is going to go from P to C, because anything after C is when my electric field begins to change. And then my electric field for this first integral is going to be the one in red minus the Q naught, because it says assume Q naught is 0. So it's going to be 1/4 pi epsilon naught r squared rho of 4/3 pi b cubed minus 4/3 pi a cubed dr. Believe that's right. Let me check. Yeah, Q naught 0, so we don't worry about it. Okay? And then our next integral is going to start at C. Right? This is C. Let's see. This one I'm drawing in green. This is C right now. And we want to go to point M. So we're just going from C to M. because M is less than D, so it's the same electric field. And we know that M is in between C and D, and we found that the electric field between C and D is 0, gets a conductor. So this is just 0. 0 dr. So this actually goes away. We don't really care about that. We just care about this first integral, and we're integrating with respect to r. So we're just integrating this portion. If I move this up to the numerator, this is r to the negative 2, right? And if I integrate this, you add 1 to the power, divide by a new power, negative 1 over r. This negative will cancel out with the negative in the front, right? So we'll be left with a positive. So v of m minus v of p can be equal to positive 1 over 4 pi epsilon naught rho 4 over 3 pi b cubed minus 4 over 3 pi a cubed. And then this is all multiplied by what we got in our integral, which is going to be this integral, right? 1 over r from c to p. So it's 1 over c minus 1 over p. So this would be our answer for this part. Now for part C, again, still assuming that Q naught is equal to 0. And now the insulating shell with inner radius A and outer radius B has a non-uniform volume charge density, rho equals CR, where C is a known positive constant. And now it wants us to find the electric field between B and C. Now what we need to know is when we ever have something like this, where rho is depending on distance, we're going to have to integrate. And remember that Q is equal to the integral of rho dV. I think that's given at the formula sheet as well. Let me check. Yeah, it's right here in case you forgot, because it's been a long time. So Q is equal to rho dV. So we're going to have E 4 pi r squared between B and C, right? So this is going to equal to 1 over epsilon naught, right? But instead of Q, we're going to have the integral of rho dV. Rho is CR. And we don't know what dV is, but we know what the volume of a sphere is, right? The volume is 4 over 3 pi r cubed. So we take the derivative of that, dV with respect to r, we're going to get 4 pi r squared. We just multiply dr on both sides, and dV is equal to 4 pi r squared dr. That's what's going to go in here. So it says times 4 pi r squared dr. And we're going to go between B and C. B and C is enclosing the entire insulator, so we're going to go from A to B. If the problem instead said to get the region between A and B, the only thing that would change is our integral will go from A to an arbitrary point R. Right? Because we're not covering the entire shell, we're only covering part of it. But in this case, we're between B and C, so we are getting the whole insulating shell. So we're going from A to B. So if I simplify this a little bit, I get C, or 4 pi C r cubed, right? So I can pull out the constants. So I can pull out the 4 pi C over epsilon naught. So now I'm just integrating from A to B of r cubed dr. So if I integrate this, let me bring down the constants, 4 pi C over epsilon naught. I'm going to get r to the 4th divided by 4, evaluated from A to B. I see that the 4's can cancel. I can divide by pi on both sides, so the pi also cancels. So then E is just going to be C over 4 epsilon naught r squared times what we got in our integral. So it's going to be B to the 4th minus A to the 4th, and this will be radially out as well. Yep, so that's the answer for this part. Now, next question, Coulomb's law. In the figure below, 4 particles form a square of sides A. Charges Q1 and Q4 are known. What are the charges Q2 and Q3 if the net electrostatic force of a particle with charge Q1 is 0? So basically we need to find what values of Q2 and Q3 make the forces cancel out. So this is Coulomb's law, which remember it's the force. So with a Q1, Q2 over 4 pi epsilon naught r squared. And it wants the center of attention to be at Q1. So it doesn't say any of them are negative, so we just assume they're all positive. So if I draw my free body diagram, from Q4 to Q1, this would be my force created. Let's draw it like this. I'm going to call this an angle here, might as well already. I'm going to call this F of 4. And then I'm going to have another force created by Q of 3. So this is F Q3. Let's put F3. Stay consistent. And then created from Q2, we're going to have a force in this direction. So FQ2. Okay. So now we need to group up our x and y components of the force. So I'm going to say f of x is equal to, I'm going to pull out the constants, 1 over 4 pi epsilon naught. And now let's see, I have 2 x components. I have the Q2 one and the one in my Q4. So let me start with Q2. If this way is the positive x direction, I see that it's going in the negative x, right? So it's going to be negative Q1, Q2 divided by the radius of the red one, right? This radius here is A. But we want the radius squared, so it's A squared. And then we need the other x component, which is also going to be negative, right? Because it's also going to the left. So it's minus Q1, Q4 divided by the radius, where the radius is this r. And if I look at this, I get r squared is equal to a squared plus a squared, right? Or this is equal to 2a squared. So this is 2a squared. And now I need the x component of that force. So I'm going to need the cosine theta. So now, to find cosine theta, there's 2 ways to do this. You can either, because it's a perfect square and you can assume they're perfect square and they have the same distance. You can assume that this angle is 45 degrees and say it's square root of 2 over 2. Or you could actually solve for it and then you end up with the same answer. I'm going to actually do it like getting the a's here instead of just assuming it's square root of 2 over 2. So then cosine theta will be adjacent, which is a, divided by hypotenuse. So if I just solve for r, this is square root of 2a squared. So square root of 2a squared. So I plug it in. And I want this equal to 0, right? I want the force equal to 0. And this can't happen with just the numbers. So for this to happen, I need the insides to equal each other. So I'm going to get negative, or I want to solve for Q1, so I'm going to move this to the right side. So I'm going to get Q1, Q2 over a squared is equal to negative Q1, Q4 times cosine, so there's an extra a on the top, divided by 2a squared times the square root of 2a squared. So that's 2a squared to the 3/2. So now I multiply by a squared, and I can also divide by Q1. So I'll get Q2 is equal to negative Q4a cubed over 2a squared to the 3/2. Now to simplify this, I can break up the bottom. So I get negative Q4a cubed divided by 2 to the 3/2 times a to the 3/2, right? Because the exponents is 3/2 times 2. So the 2's go away. So it's just a cubed. So the a cubes cancel. So I'm left with negative Q4. And then 2 to the 3/2 can be rewritten as 2 to the 2 over 2 times 2 to the 1/2, right? So then this is just 2 times square root of 2. And we can rationalize this. So this is equal to negative Q4 root 2 over 2 times 2, which is 4. So this is what Q2 needs to be. And if you make the assumption that cosine was root 2 over 2, this would have been, you would have gotten the same answer. But it would have just been a lot quicker. Which I'll actually do that in the second part, because that's only the first part. So let me just say this is square root 2 over 2. So now for the y component, I'm going to have 1 over 4 pi epsilon naught. And now let me group up the y components. So I have Q1 and Q3, and it's going up in the positive y direction. So this is Q1, Q3 divided by the radius. This radius is A. This green line I'm drawing, it's A. But we want it squared, so it's A squared. And I need the second y component, which is the one in black to the left. It's still going up, so it's positive. So it's plus what? Q1 and Q4 divided by the radius, which is 2A squared, cosine theta. But now let me just show that this assumption does work. Square root of 2 over 2. So I'm just have it as times square root of 2 over 2. I need this equal to 0. And I want to solve for Q3 is what it was, right? Yeah, Q3. Yeah. So Q1, Q3 over A squared is equal to negative Q1, Q4 over 4A squared root 2. So I multiply by A squareds and go away. I divide by Q1, that goes away. So Q3 is equal to negative Q4 root 2 over 4. Which again, we got the same answer we got over here. Which, they're both correct, but this step is just a lot easier. If you happen to recognize that it's a perfect square and you know that the angle is going to be one of the Pythagorean triplets, it's going to be a 45, 45, 90. If not, you can solve it the way we did it over here originally, and you'll still get the right answer, so it doesn't really matter that much. But yeah, not too bad. Coulomb's law. Now number 4, 2 straight conducting rails form a right angle. A conducting bar with resistance R. So the bar is resistance. Is in contact with the rails. Excuse me. It starts at the vertex at time equals 0 and moves up at a constant speed of v0. There's a uniform magnetic field of magnitude b0, which is directed out of the page. And it gives us the formula for the area of a triangle in the back over here, just in case you forgot, as well as the cosine 45 and all these others as well, which we are going to use right now. Now part A says, find the direction of the current in the loop, and it wants us to explain our answer. So basically, to answer this part, we're going to have to use Lenz's law. So if we take a moment to analyze what is happening with the picture, it's saying that the bar is moving up at a constant speed of v0, right? So eventually the bar is climbing like higher and higher, right? Pretty much. So as that's happening, the area enclosed here is increasing, right? So area is increasing. And because the area is increasing, that means that the flux is also increasing. And when that happens, B self is in opposite direction of the B field. So B self is, so B is out, and B self is going to go the opposite way. B self is going to be into the page, which means the current is going to be, well, if I put my thumb into the page and I curl my fingers, my fingers are curling in the clockwise direction. So current is clockwise. And this is Lenz's law. So Lenz's law. And that's how you would prove that. Now for part B, find the current through the bar as a function of time. ignoring self-inductance. So for this one, or like anytime you see some sort of bar or like a box or something like this, you're going to have to use Faraday's law. So it's going to be the closed loop of E dot dr is equal to negative partial respective time of the flux. So let's see. Let me draw my current first. So we determined that current is going clockwise. So current is going like this. This is current. And then by convention, I'm going to make ds always go this way. So it points out of the page. So I want to find the flux, which is B dot ds. Well, the B is constant, so it's just B naught. And then I'm just left with the area of ds. Well, the area of this, of a triangle, is 1/2 the base times the height, right? So it's gonna be B naught over 2 times the base, where let me give this rod a length L. So times the length, and then we're gonna have to multiply it by the height of the triangle, which in this case I'm gonna call y. Which if I split this down perfectly like this, I will get this hypotenuse here, which is this is gonna be y. And then ds is pointing out and b is pointing out, so the dot product is gonna be positive. So I can leave it like this. But I don't know what L is. But because of the way I just split the triangle right now, let me draw it on its side so it's a little easier to see. Yeah, that's good enough. So we have a 90-degree up here in red, right? It's the 90 part. And then we have this bottom part here, which we knew was 90, but I split it into 45 degrees. So now this is 45 degrees. So this is also 45 degrees. And then with the way my triangle is orientated, this is going to be L over 2, because I split it in half, and this is going to be y. So to find what L over 2 is, I can get the tangent of this angle. So tangent of 45 degrees, which is going to be adjacent, which is L over 2, or hypotenuse, which is y. So this is going to be L over 2y is equal to this, or L over 2 is equal to y tangent 45 degrees. Tangent 45 degrees is 1, so L over 2 is equal to y. So then my flux is now B naught y squared. Now I need to take the time derivative. So d dt of the flux is going to be the power rule, so 2b naught y times the chain rule, so it's going to be dy dt, because we're taking it with respect to time. And dy dt, the velocity is going up, and y is also moving up, so this is positive v naught. But we can't just leave y as it is. But we know the velocity, and we know that y, which in this case is the position, is the integral of v dt. So this is simply v naught t. So the time derivative is going to be 2 b naught v naught squared t. Right? So the time derivative. And now we just have to put everything together. So if I go around my loop, I'm going like this, right to the left. But current is going to the right. So I'm going to have negative IR, right? And negative IR because the rod has a resistance R. And this is going to be equal to negative from the law, right? Right here, the negative of the flux that we found. So it's going to be 2 B naught V naught squared T. And if I solve for current, I get that I is equal to 2 B naught V naught squared T over R. And like we said in the beginning, in the clockwise direction. So the hard part here was understanding, it was basically finding the length because it wasn't given. You have to use tangent. Easier to see if you split it down the middle. Okay, now for part C, consider the time moment when the bar has a length b. So in this case now it is giving us an appropriate length. What is the magnitude and direction of the force that must be applied to the bar to have the net force equal to 0? And we're going to ignore gravity. So for the force equal to 0, we basically want the force created by the bar to be cancelled out by another force. And in this case, we're dealing with currents, right? So to find the force, when we're dealing with current, it's going to be it's actually dF, ds cross b. But when b is constant, in this case it is, it's just b naught, we can just write the force as force is equal to I ds cross b. And this is I, right, the current. ds is the length, or like what we're going through, which in this case is the rod, which has a length b, and then times the magnetic field, which is b naught. But now to determine the direction, we go in the same way the direction the current is going. So my ds vector is going this way. Right, it's ds because current is flowing from left to right on the rod. And b naught is out of the page. It's out of the page, right? So I'm doing ds cross b. So I put my palm in the direction of ds. And I curl my fingers out of the page. I get my thumb is pointing down, right? Force is down. So if I want to create an applied force to make it equal to 0, I'll just make the force go up. So then force applied is going to equal to I, B, B naught up. Just in the opposite way to make it cancel out. Now for number 5, here we have 2 wires, each carrying a current, 2 different currents, I1 and I2. Wire 1 consists of a circular arc with radius r and 2 radial lengths. It carries a current I1, there's an angle, and wire 2 is an infinitely long and straight wire. Excuse me, which is a good indication that we're going to use Ampere's law. It has a distance r2 from the center of the arc, and it wants us to find the magnitude and direction of the magnetic field created by these 2 points. So for the left side, we have 3 regions, right? We have this straight wire, then the arc, and another straight wire. In this one, we're going to have to use Biot-Savart's law, which is dB equals mu naught I over 4 pi of ds cross r cubed. ds cross r divided by r cubed. I had him flipped. So what we can see is that region 1 and region 3, the magnetic field here is going to be equal to 0. Why? Because if I draw my ds vector, right, ds is going this way. My r vector is also going this way. So the cross product is going to give me 0. And the same thing applies to the second wire. My ds vector is going to go this way. And my r vector is going to go the other way. But it still doesn't matter. They're still parallel to each other. So the cross product is going to give you 0. So that's why for region 1 and for region 3, the magnetic field is 0. So we only have to deal with the circular arc portion. So let me write this down. Region 2, dB equals mu naught I over 4 pi. I'm going to call ds, let's make it go this way. Let's pick up points. Then my r vector is going to go like this. So the cross product would just give me ds times the radius, which is r, divided by r cubed. And the direction, so it's ds cross r. So I put my palm on ds, right? And I curl my fingers towards r. I would get that my thumb is pointing out of the page. right? But now I need to find B, so I need to integrate both sides. So B is equal to mu naught I over 4 pi r squared times ds, where in this case, it's not like a perfect circle. So we need to recall that ds in this case is equal to the arc length, which is r theta. In this case, the radius is going to be a big R, so this is r theta out of the page. So if I simplify this a little more, or this is actually current I1 as well, I should put that too. So I would get mu naught I1 divided by 4 pi r times theta out of the page. Now for the long wire, this is where we would apply Ampere's law, which is the closed loop of B dot dr is equal to mu naught I So I would get B 2 pi r is equal to mu naught I, or B is equal to mu naught I over 2 pi r. But in this case, we have a specific radius, right? This is going to be r over 2. So we just plug it in here. So we get mu naught I over 2 pi r over 2. We see the 2's cancel. So we're just left with mu naught I over pi r. And now we need to determine a direction. Well, if I put my fingers along the wire and I curl them, when I come to the left, I see that this is coming out of the page. And when I come back around, I get that my fingers go into the page on this side. So this is going to be into the page. So my answer is going to be B total. Let me put a B total. This is going to be mu naught I1 over 4 pi r theta out of the page plus mu naught I2 over pi r into the page. This should be I2. Right, because the current's not the same. This one has a current of I2. So yeah, that'd be the final answer. So yeah, again, to find the direction of Ampere's law, you put your thumb in the direction of the current, and then you curl your fingers. You get that your fingers are pointing out on the left side, and then when you curl back, now they're coming in. So that's how we found that it's going in. For number 6, in the circuit below, we're given all of these constants. The switch is kept at A for a long time, and it wants us to find the current through the resistor and the charge in the capacitor. Now the key thing in this part A is that it said it's kept at the point A, so like this, for a long time, which means it's in steady state. So if I look at the circuit, well, I see a battery, right? So I'm just going to make the current come out of the positive side. I'm going to say this is plus Q and minus Q. And at switch A, we don't really care about what's at the bottom, right? We just go through here. But the thing is, we know in steady state that current cannot go through a capacitor. And in here, that's the only path that we have in our circuit. So because of that, we can say that current is equal to 0. Because there's no way it can go through the capacitor. Excuse me. And now to find the charge on the capacitor is where we can use a loop. So if I go my loop like this, let's say, loop 1, I will get, there's no IR, right? Because there's no current. But there is charge on the capacitor. So I touch the plus side of the capacitor. So it'll be Q over C. I ignore the second resistor again because there's no current. And then I end up touching the back of the battery. So minus V is equal to 0. Or if I want to solve for Q, I get Q is equal to CV. So that's it for the first part. For steady state, it's pretty easy because there's no current that can flow through, so it's not that bad. For part B, now at time equal to 0, the switch is now switched to be at position B. And starting from some famous law, derive the equation that describes charge Q on the capacitor as a function of time. So for this one, we're going to have to use Faraday's law, which is a closed loop of E dot dr is equal to negative partial respect to time of the flux. And let me just redraw the circuit to see what's happening. So we have a capacitor plus Q minus QC. We have R2. And then we have the coil. So this is what we have. So I'm going to go around the loop this way, because that's how the book does it, right? DS, and it goes out of the page. And then at time equal to 0, there's going to be 0 current. But then eventually there's going to be some current leaving the capacitor. And I'm going to choose for that current to flow out this way. Why? Because I want the current to go into the positive side of the capacitor, like by preference. So I can say I is equal to dq dt. Okay, so now let me find the flux. In this case, the flux is going to be created by self-inductance, created by the coil. So it's going to be plus or minus Li. Now, determine if it's plus or minus. Well, we're going to have to do the dot product of ds and B self. In this case, ds is pointing out, and my current is going in the clockwise direction. For that to happen, my thumb either has to be out of the page or in the page. If I go out of the page, I get that my current is going in the counterclockwise direction, which is not what I drew. So that's not the B self for me. So in this case, B self is going to be into the page, right? Because I put my thumb into the page. Now the current, my fingers curl in the clockwise direction, which is the same way as my current. So that fits my convention, the way I drew the current. So then B self and ds are going the opposite way. So dot product is going to be negative. So it's going to be negative Li. And I take the time derivative of this flux. It's going to be negative L di dt. So now I can go around the loop. So I would get negative IR2, right? I'm going the other way. And then minus Q over C is equal to negative, from the law, negative, and then my flux, negative L di dt. So I'll get negative IR2 minus Q over C is equal to positive L di dt. If I move everything to the right, I get L di dt plus IR2 plus Q over C is equal to 0. But I want to solve for capacitor, for the charge, so I need to write all i's in terms of dq dt. Again, because current's going to the positive plate of the capacitor, I is positive dq dt. So then the final version of this is going to be L d squared q dt squared plus dq over dt of R2 plus Q over C is equal to 0. And we can't really solve this like that easily, so that's why I just wanted us to find the equation. But now for part C, if we neglect R2, solve for the charge on the capacitor as a function of time. So now we're going to solve if R2 was, like, we ignored. So then we're going to be left with L d squared 2 dt squared plus Q over C is equal to 0. And now we can recognize this as a second order differential equation. Well, we recognize it first if we divide by L on both sides. So d squared 2 over dt squared should be dt plus Q over LC is equal to 0. So for this one, I'm going to make a guess that Q, instead of alpha e to the negative t, for these second order differential equations, we're going to have A cosine omega t plus B sine omega t. So how we start this is, let me write the steps as well. So you can find A using Q equal to 0. So Q at t equal to 0. You plug in 0 for all t's. Cosine of 0 is 1. Sine of 0 is 0. So A is equal to the initial condition, which in the beginning we said the initial charge was CV. So this has to equal to CV. So then we can say A is equal to CV. Now the second step is to find B using I equal to 0. But we don't have the equation for I. We know I is dq dt. So then I t would be derivative cosine is negative sine, so negative a, and then chain rule, omega sine omega t, and the same thing for the right side, derivative sine is cosine, and then chain rule, b omega cosine omega t. And then I of 0, I would get 0 plus b omega, and this has to equal to the initial condition of the current, which we said was 0. We can divide by w, and then we just get that b is equal to 0. And then to solve for omega, or the w, we would plug it back into this equation in red. But I don't have the second derivative, so let me get that real quick. So the second derivative would be derivative sine is cosine, then chain rule again, so negative a omega squared cosine omega t, derivative cosine is negative sine, negative beta, then chain rule, omega squared sine omega t. And then we just plug this in over here, back to the original equation. So I would get negative a omega squared cosine omega t. But I'm going to leave this b sign out because b is equal to 0, right? So I just have plus q, where I said q was a cosine omega t, plus b sine, but again b is 0, so just plus 0 over LC, and this is equal to 0. Now let me plug in what I found for a, which is just CV, so negative CV omega squared cosine omega t plus CV cosine omega t over LC is equal to 0. I can divide by cosine, I can divide by CV, so I get negative omega squared is equal to negative 1 over LC, or that omega is equal to square root 1 over LC. Then I can finally write the final equation. So QT is A, which was CV, right? Cosine of omega t. So it's just t over square root of LC. Yeah, that's how you would solve second order circuits. Just make sure you make the guess of A cosine omega t plus B sine omega t. Now for the last problem, in the circuit below, VC and R are given, time equal to 0, the switch is closed to begin charging the capacitor. And it wants us to find the charge in the capacitor as a function of time and the current in the circuit. We want to neglect self-inductance. So there's a battery, right? So let me just close the switch. There's a battery, so I'm just going to make current come out this way. I'll make this side plus Q, this side minus Q. I'm going to go around the loop this way by convention, because again, that's how the book does it. So in this case, there's no external magnetic field, and we're ignoring self-inductance, so the flux here is going to equal to 0. And again, we're using Faraday's law, so E dot dr is equal to negative partial respect to time, B dot ds. But this is 0, so we don't really care about that. So now we just go around the loop. So if I go around the loop, I'm going to get negative IR, right? And then I'm going to get minus Q over C. And then I get the positive part of the battery, so that's plus V is equal to 0. Then I can move these two to the right. So I get IR plus Q over C is equal to V. But I want to find charge. So I need to write I in terms of Q. And I is going into the positive part of the plate. So I is positive dq dt. So this is dq dt R plus Q over C is equal to V. And we can see that this is a first order non-homogeneous equation, which means our guess is going to be a Q particular plus Q homogeneous. Q particular is in steady state, So that means all time derivatives are equal to 0. So then QP, so then I would have 0 for the time derivative, right? Plus Q over C, but I'll call that QP. So QP over C is equal to V, or that QP is equal to CV. So that part is pretty easy. But then for QH, we assume that it has a solution of alpha e to the negative beta t. So then, wherever I see Q, I'm going to plug it in. So the derivative of alpha e to the negative beta t is going to be alpha e to the negative beta t times chain rule, which is negative beta, times the r, plus alpha e to the negative beta t over c. And this is equal to 0 because we're saying it's a homogeneous. Homogeneous means equal to 0. And in this part, you always solve for beta. So I divide by e to the negative t, divide by alpha. I get negative beta r is equal to negative 1 over c, or beta is equal to 1 over rc. And then to solve for alpha, we just plug it back into q of t. So q of t is equal to cv plus alpha e to the negative beta t, which is negative t over rc. And then in this part, we always say find the initial condition when t is equal to 0 to solve for alpha. So I would get cv plus alpha e to the negative 0 over rc, which is 0. And then we're going to say that the charge here is going to be equal to 0 because initially the switch is closed and it says it's going to begin charging. So originally there was no charge. So we set this equal to 0. So if we get alpha is equal to negative CV, then Q of t would be CV. If I factor everything out, I would get 1 minus e to the negative t over rc. But that was just the charge. The question also said to find the current. Recall again, current is I into q dt. So simply just take the derivative of the answer that you found. So then current is going to be CV negative e to the negative t over rc times chain rule. So negative 1 over rc. Negatives become a positive. The c's cancel. So current is equal to V over R e to the negative t over rc. Now part B, it wants to find the electric field between the plates of the capacitor as a function of time, given that the area is A. Well, the electric field for capacitors is sigma over epsilon naught. In case we don't have that memorized, the way you can, I guess, derive it is if you draw capacitors. You take a cylinder and you get a cap here. It's a conducting plates. So the electric field here is going to be equal to 0. But here we're going to have EA. So we'll have EA is equal to Q over epsilon naught, right? It's using Gauss's law. But Q is the integral of sigma A. So then I will get EA is equal to sigma. The area for that little cap will be little a over epsilon naught. So I get E is sigma over epsilon naught. That's how I get that. But now I don't want sigma. I want it in terms of the charge and the area, given that it's area of A. So using this same equation, I'll get Q equals sigma A, or sigma equals Q divided by A. So I get Q over A epsilon naught. I have Q that I solved earlier. So this is CV, 1 minus e to the negative t over RC divided by area epsilon naught. And this would be the electric field. It's equal to E. Now for the last part, I want to find the displacement current between the plates. Recall displacement current is epsilon naught partial respect to time of the flux of the electric field. So let me find the flux of electric field. So the flux of the electric field is the integral of E dot ds. I know what E is. E is this. So it's CV 1 minus e to the negative t over RC over area epsilon naught times ds, which is just the area. So that's just A. So then this simplifies to CV 1 minus e to the negative t over RC over epsilon naught. Right, because A cancel. And I'm multiplying by an epsilon naught. So let me just do that right now. Because I multiply by epsilon naught, and this also cancels. So I'm just left with CV 1 minus e to the negative t over RC. Now I need to take a time derivative for that. So ddt of the flux of E. I multiplied by epsilon already, so let me just write the epsilon naught as well. So if I take the derivative of this, I'm going to get CV. Derivative of 1 is 0. I'm just left with the E. So negative E to negative t over RC. And the derivative of that is going to be negative 1 over RC. So one of the C's are going to cancel. Negative becomes positive. So this is equal to V over R e to the negative t over RC. This is displacement current. And one thing you should recognize is that the displacement current is the same as the current. It's because, yeah, that's true. We're going to have one or the other. So we should know that current should equal to displacement currents. So I guess that's a way you can check that you did your work right as well. If you see that your displacement current is the same as the current, then you probably did it right. All right, well, that was all the questions on this exam. Hopefully it helps, and good luck on your finals.